what I want to mention to start with is that hydro is the oldest sustainable technology and still contributes very significantly to the power grids right across Canada. However, in the discourse in the public realm, on television, and in the political realm, whenever sustainable power is mentioned, or renewable power, there's no mention of, little mention, I should say, of hydro. And when hydro is talked about, often it's talked about in a very ambivalent way. So I want to sort of give the story of hydro today, and particularly show how it can contribute positively to the secure operation of power grids. So we'll start with forward. Yep. I'm going to talk on these 5 topics, concluding with a brief discussion of the question, is hydro sustainable? The governing features that which are required for successful hydropower development is a suitable hydrologic regime, enough water, in other words, enough rainfall, and suitable topographic features where the head can be developed. Typically, hydro plants are located at anomalies in the topography. I'll talk briefly about multi-purpose developments, which I think are unique to hydro as a renewable energy source, and a little bit about run-of-river versus hydro projects versus storage. This is a picture on a reconnaissance in the Rio Sabanilla River Basin in Ecuador. They have 2 seasons in Ecuador, rainy season and rainier season. They have a lot of relief, so it's an excellent place for looking for hydro developments. Contrast this to an arid zone. This is Sneer Lake towards the end of winter. The total precipitation in this part of central Northwest Territories is just 250 millimeters, scarcely 10 inches of rain, of snow and rain together, and a runoff of about half that amount. I'll take you through a tour of some different sites. A canyon site offers the opportunity to develop head by building a rather small dam. This site in Newfoundland, at the bottom of the river, it's scarcely 3 meters, 3.5 meters wide at the bottom. The solution to this we found was a small concrete arch dam which raises the water level about 43 meters. This is one of the rare structures of this kind in Canada. I think it's only the 4th, going back to 1829. The first of arch dam is at Jones Falls, just north of Kingston. Another approach, another configuration that is favorable for hydro is utilizing building a shortcut around a river bend. Here there's a bend, I think probably altogether maybe 60 kilometers. The accumulated drops through the bend are then exploited by a development starting with an intake, delivering the flow by tunnel to a power plant. This is the largest project in Nepal. Oops, no, that's the wrong one. Coming back to Newfoundland, this is a high head project. Much of Newfoundland is a plateau. Many of our hydro projects exploit the level between the lake, the top of the plateau to sea level. In this case, this project has a head of 386 meters. To see larger heads, you have to go to the Rocky Mountains. Nothing east of the Rockies approaches this. It was interesting as a design which had an online tunnel through most of the length of the flow, with pressures up to equivalent of 386 meters. So it was a Canadian first at the time. This is another site close to St. John's, where the head is developed through a set of rapids. So you can see, you can see the rapids here coming down, and this site picks it up from the end of a canal, pipeline. Because a pipeline is relatively high, you need a surge chamber to control the transients over water hammer when you shut the plant down. Instead of decelerating the water all the way up the pipe, you just decelerate it for this portion and up the tank. Now this is a type of development normally associated with waterfalls, and in concept very similar to Niagara Falls. I would have shown Niagara Falls, but it was just too noisy. There was too much junk on the Google photo. Here we have a series of fairly large falls there, and the river, which you pretty well can't see anymore. And the project develops the head between Hines Lake, which is a fairly substantial lake, maybe 50 to 60 square kilometers. Now this is a control structure here, then a canal about 8 kilometers long, and the water is then transferred to a power plant at this bay of Grand Lake. So we're going from one plateau to a lower level. And Niagara Falls is similar. You take the water off at the head of the rapid, so to speak, and deliver it by a canal or tunnel. In the case of Niagara Falls, on the Canadian side, it's primarily tunnel, and the American side is primarily canal. Multi-purpose projects are a feature of hydropower development. In this case, it's in Alberta, near to Lethbridge. My son actually is in charge of running these plants. There are 3 power plants that operate on the main canal of the St. Mary's River irrigation system. They operate just during the season when there's a demand for water for agriculture, so they usually shut down in the winter. If anyone has a few million burning a hole in their pocket, there are a couple other locations where there are drops in the system, where there's a capacity from 7 to 12 megawatts or so. So think about it. This is a picture of the Tamingor project in Malaysia. It was designed by Shawinigan Engineering of Montreal and built in the late 60s. It's primarily for power, but also provides flood control. This flood control is obtained by handling floods that go through the reservoir, partially by storing the flood volume, storing some of the flood water, and then releasing the water at a lesser rate than would have occurred in nature. And this, the design they eventually selected has an overflow spillway. It's safe. It's inherently safe because it has little or no maintenance attached to it, no mechanisms to fail, no problems with operators going to sleep. It's purely automatic. The storage is obtained by allowing water in the design flood to raise 4 meters above the normal reservoir level to a volume of something like 850 million cubic meters. The reservoir surface is about 150 square kilometers. The project has a capacity of 308 megawatts, and the fall or the head between the reservoir and the power plant, or the average fall, is 101 meters. The water level is a little bit tricky to see, but when it's full, water will be right up here, and this is This is your sort of, we call that a kind of a bathtub spillway. I wanted to give you a contrast between a high head project and a low head project. This is a project in the Himalayan foothills in Punjab state. And there's a couple hundred meters of fall between a canal that snakes along the side of the hill there and the power plant. It has a capacity of 3 megawatts, a drop in the order of 200 meters and a design flow of about 1.8 cubic meters per second. Contrast this with a small hydro plant in Northwest Territories, where the capacity is about 50% higher, but the head very small, and the flow, by contrast, significantly larger. So this is kind of trying to set some parameters. This is one of the most famous plants in India. This is a Terry project. It's a very, for a embankment dam, it's very tall. The storage reservoir is about 60 kilometers long. And I think the present configuration has, oops, I'm going the wrong way, wrong button. It's about 500 megawatts, but a re-regulating reservoir is being built downstream, and additional 500 megawatts of peaking capacity will soon be added if it's not done. Contrast this with the Union Power Company, Newfoundland, which has half a megawatt vis-a-vis 1,000. I show this. It's rather nondescript little building, but it's interesting because it was built by a company set up by the Fishermen's Protective Union to provide electricity to the people who lived in Port Union. And it's the only project in the world that I'm aware of where you could pay your electricity bills in goods. So if you didn't have cash, you would fill up your wheelbarrow with the appropriate number of pounds of saltfish and take it to the plant office. Just before going to this, I was going to mention, we've talked about multi-purpose, and we've talked about flood control and hydro, irrigation and hydro. There are several examples in Ontario, but I couldn't get a good photo of navigation and hydro, small projects, several small projects in both the Trent and the Rideau canals. And a rare example of water supply and hydro, which is in Labrador, a very small plant. If you can incorporate in your development some measure of storage, you can go a long way to increasing the utility of a power plant. Now, I'll just go quickly through the range. Oops, oh my, I'm not very good at this. Daily pondage is just is associated usually with run-of-river plants, providing just enough storage so that the distribution of flow can be sort of adjusted or regulated so that the maximum flow goes through the plant at peaking or during the period of peak load on the system. A small hydro example of this was a proposed project in Newfoundland. With this reservoir, again, it was operated as run-of-river, but with a larger reservoir, it had the capacity of absorbing substantial inflows and hence increasing the utility of the output. When you come to intermediate-sized reservoirs, and the intermediate sizes in the ratio of live storage, because of course Tarbella is huge compared to Snare Rapids, these tend to be seasonal. In the case of Snare Rapids, annual, yeah, let's say the season was 1 year. Hines Lake is at the limit of this classification, is a multi-year has multi-year regulation and should carry the firm up guarantee power through a 3-year period of drought. Cat arm is very similar. There's just a small difference in the ratio. When you go to LG2, I think you're looking at ability to guarantee or firm power over a 5-year period. You expect from your modeling that a 5-year period would be the worst that you'd, well, have, say, maybe in a 1 in 100 years, might be a little bit worse. Aswan, they say will never spill, but I don't think any hydrologist is going to stake his reputation on that. I wanted to talk a little about other renewables. Now, I'm not an expert in other renewables, so if you have any questions or want to challenge me, just remember and we can talk about it later. So I'm looking at 2 issues. We'll look at comparing the renewables on the basis of the characteristics of the developments and then on the basis of their technologies. I've looked at 3 sort of issues: the variability. Basically all natural power sources are variable, depend on wind and weather. In the case of hydro, it's the variabilities of the hydrologic regime that are at play, the wind regime for wind power and the solar regime. Typically, these sources provide little or no firm energy, and in sort of economic or in an intuitive sense, function mainly as energy savers. So in a combined system, like we have in Newfoundland, if you can, when you got lots of water, you can shut down or cut back a lot on thermal power production, which is now costing us 15 cents a kilowatt hour. It's pretty damn expensive. Second factor is persistence, and this really highlights the situation for hydro. Hydro power plants are almost always on perennial rivers, and if we use this ratio of the flow equaled or exceeded 90% of the time over the mean, you can see this varies quite widely. The variation really relates to the nature of the watershed. This is based on a river fairly typical of Atlantic Canada, though it's from Quebec. And this is a river from the Northwest Territories, which has huge amounts of natural storage, one lake after the other. Persistence is not, I think, associated with either. When it's night, there's no solar power. And when there's no wind, there's no wind energy. I'm not sure how useful predictability is, but if I'm a power system operator, it might be nice to know over the next little, looking forward, what I can expect from my hydro stations, wind stations, or my solar generators. In the case of hydro, the watersheds inevitably include some storage features, some features which lag the flow so that when it stops raining, the river doesn't stop flowing. So these features are lakes, bogs, and groundwater. I'm sorry, this is a rather noisy chart, but it's got a few points. I decided I couldn't really cut it down too much. I'm looking at these 5 factors. Maturity, I'm suggesting the state of the technology. In the case of hydro and wind, I'm saying the basic science is well known. They're not perhaps as much opportunity for major improvements that could have a large-scale impact on the technology. I think the solar is still a work in progress. Robustness, I'm primarily thinking about how reliable and how dependable the generators are. Hydro, they operate pretty well without trouble from the weather. I have put this issue though because in parts of the South Asia, the Himalayan regions of India, Pakistan and Nepal, sediment is, waterborne sediment is a big issue, and it plays hell with the turbine wheels. We look at wind. Again, there are sort of a couple limitations. For very low speeds, the wind energy, you can't operate the windmill effectively. And for high speeds, you start to risk the thing blowing apart. So you have upper lower limits of operation, and cold weather issues are also a concern. This is a nominal figure. The fellows in Ottawa tell me that with special designs, the operating temperature may be reduced to -30, maybe -35. There are not a lot of moving parts with hydro, with solar, so it seems that this should be pretty robust. The one thing I was told, and I didn't get it put up, is that the inverters associated with solar have a life of about 8 to 10 years. So you don't replace your system, but you have what we call in hydro jargon interim replacements. Those components which are short-lived are replaced as required to keep the system up and running. Another measure of robustness is, in the case we're looking at the life of rotating equipment. In this case, it's mainly turbines and generators. We had one turbine in Newfoundland that was installed in 1911, turbine runner, and taken out of service in 1986. It was pretty ratty, but 75 years in operation, not too shabby. The equipment is about 20 years, but a gearbox and bearings, I'm told, can be a bit of a problem, especially where there's a sort of gusty, and I think where the climate is hard, as we say in Newfoundland. Dams and structures in hydro are given an economic life of 50 years, but dams in particular may last well over 100. The numbers shown for wind, the towers and the foundations, I think 40 years is a bit of underestimate. I'm sure they're almost in the same ballpark as hydro. The idea of availability, and I've joined that with the word readiness. I'm saying is, where there's a flow, what percentage of the time can I be able to load my equipment? And hydro, I've shown 95 to 98% of the time. 2% of the time is 1 week shutdown. And where I worked, it was a practice to shut down each plant for a week for a detailed inspection and overhaul. If you had unscheduled shutdown of another week, it would be 96. So I think it's probably better than 95. I have put the question mark here because this is what the manufacturers propose, but I've several times traveled in the vicinity of the name of the place slips me, in western Alberta, the big wind farm there. Several times I've been by it. Pincher Creek, big development. I would swear that every time I was there, at least 10% of the windmills were not turning. So my instincts tell me 98% is dreaming. 90% might be better. Again, when it's sun shining, I think a system with no moving parts, it should be pretty good. Keep the dust off it, I guess that's about all. Energy capture, this is, I'm saying, and this I'm thinking in terms of the amount of energy that I can capture from, because remember your energy input is variable. between within the capacity of the unit. So in hydro, run-of-river, typical amount is 50% of the flow energy available can be utilized. With long-term storage, greater than 80% is quite a possibility. With wind, it seems to be in the order of 13%. Now this is a figure I got from fellows in Ottawa. I'm not sure if how it's defined. So that figure needs perhaps a little bit more work in it. When I talk about the economics, I put a whole lot of words there, but what I'm really trying to demonstrate, or the message I'm trying to give, is that by and large, both wind and solar equipment can be highly standardized, and the impacts of economies of scale are much less of a problem. When you're looking at hydro, great efforts have been made to standardize design of equipment, so you can buy water-to-wire packages nowadays for small hydro, in which the design of the turbine, generator, and all the control equipment is in one package based on standard designs. Civil works are unique. The consequence is hydro is much more sensitive to economies of scale, and for small hydro projects tend to come in sometimes rather too high. So it's a challenge to the business. This is a big part of my proposal, so we'll go through it. These are the issues, and we'll talk about each in turn. Where you have a system with large storage reservoirs, there's a possibility of providing some virtual storage. Now, the way I've been thinking about this is looking at wind plus hydro, but it could be run-of-river plus storage hydro as well, or solar plus hydro. Essentially, on a windy day, when your windmills are chugging out great scads of power, you can cut back on the operation of your hydro plants and store that water. When the winds are slack, you can take that water out. So you've got almost a cost-free exchange. That energy that you produce, energy you save one day, you produce the next. This is a strategy that Hydro-Quebec is exploiting because there's an interest in Quebec to develop wind. It's seen as a factor in rural development. If you go to the Gaspé, there are quite a few little windmills, 2 or 3 here and there. Hydro units can be very quickly put online. And I'm just more or less showing the difference of the delays. If you're trying to crank up to meet a peak load with nuclear, well, forget it. It's very questionable if you can really do very much with thermal either. Gas turbines and diesel generator gensets, diesel engine power generators, can generally be up and running in about 15 minutes. Hydro, if it's spinning reserve, can be 5 seconds. Generally, we're talking seconds to minutes. If you have to open a valve, then it takes a bit longer. So that's an asset. So we look at frequency control, the ability to rapidly load and unload generation from hydro helps to mitigate frequency swings. You want to try and keep your power at 60 cycles. You don't want it to deviate very much. Hydro generators generally contribute more inertia to the system, so any disturbance of the system can be at least partially attenuated, because that energy gets stored by the inertia of the hydro generators. Generators and sometimes work as synchronous condensers to help correct the system load factor. Now, I'm a civil engineer, so this is really kind of scary stuff for me. But these are contributions to frequency control just to give you an idea of the quality of power that is expected. This is advice I got regarding supply to a mining load. Here we were looking at adding 2 or 3 megawatts suddenly on a load of about 14. And it was judged that it would be appropriate if the frequency didn't stayed within plus or minus 3 hertz. These are the German norms, much more tight.
At the National Grid
This is
Control
it.
Centre, National Balancing Engineer Simon Jeffcoats on duty.
This is from England.
The wall in front of him is his view of Britain from above. The country's been tipped on its side, and every high-power electricity connection from the far north of Scotland to Cornwall has been mapped out in loving detail. But Simon is bracing himself for the most difficult moment.
I don't know how this is.
By watching his enders. When the credits start to roll, he's going to have to deal with a massive surge in electrical demand, what's known as a TV pickup.
We're
Expecting a pickup of around about 3 gigawatts, which is 3,000 million watts, or equivalent to 1.5 to 1.75 million kettles going on. So we expect the demand to pick up over a period of about 5 minutes. Power surges like this are unique to Britain. No other country in the world switches on so many kettles in so short a time. To cope with the strain, Simon has had to put specialised power stations on standby as far away as Snowdonia and Scotland. These hydroelectric plants can set thousands of tons of water plunging down the hillside at a moment's notice, generating huge bursts of power in a matter of seconds. But Simon is also having to ask our neighbours across the channel for a favour. To assist us with the end of the EastEnders, we have the French link picking up, and they are picking up 600 megawatts, 100 megawatts a minute, so that's again a very rapid response. Simon is slave to this flickering frequency indicator, which he has to keep as close as possible to 50 hertz. If there's not enough power in the national grid, it drops off the scale. Too much, and it shoots off the other side. And he has to judge his timing perfectly, even if the BBC isn't quite working to schedule. We've been notified a time at the end of the programme, and it hasn't actually finished at that time. Which means Simon fires off instructions from his keyboard. On the other side of the country, vast turbines rumble into life. He's up to 150. I've just instructed him up to 300 megawatts now. The Snowdonia was up to 90 megawatts. It's still output. French power on now. 2 minutes into the TV pickup, and it looks like there's going to be more than enough power to go around. And then suddenly, there's a problem. What is it? What is it? French thing? There's a trip on the additional supply from France. The frequency has dropped dramatically. Simon has just moments to cover the sudden shortfall. one more hydroelectric plant online. Then, once more, the supply heads back into the safe zone.
It was an immediate decision. As soon as the frequency dropped through 41.8, I had to react.
The delicate balance of our electricity supply has been restored, for now. Across the country, a million kettles keep on boiling.
The quality, unfortunately, wasn't that good, and with the light, perhaps you saw less, but the story, I think, come across loud and clear. Interestingly, virtually all the things he's adding are hydro. Denoric is a famous peaking pump storage plant in Wales, and the others I know less about. So let's continue. It's just the story was about load coming on very rapidly. We had a problem in Newfoundland back in the late 60s, early 70s. We had a large phosphorus plant with electrolytic smelters of about 50 megawatts. The load in the system, peak load, was about 600. So these were, on any day, 10 to 15% of the load. And these would fail just like that. It was crazy. And at the other end of the system, we had two pulp and paper mills. So when the system lost load, frequency went up, this pulp and paper machines sped up, and either a weakness was introduced in the paper or the paper tore altogether. And it's a mess. These are big machines. When you're finished and you've got a few hundred feet, 100 feet maybe, paper from here all the way back to the end of the building that you got to clear out and somehow patch on the roll again. It's a pain. So eventually a procedure was worked out. Before they pulled the plug at the phosphorus plant, they phoned the other guys and they could drop the connection to the system and manage their paper machines that way. But the need for control has a lot to do with the equipment. If you have speed-sensitive machinery in your system, like pulp and paper machines, you have this frequency control is very important. There's also voltage control, which I know less about. I know in Nepal, everybody had it between their computer and the power system. You had a spike protector. It was really a sort of indigenous electronics industry. A bunch of fellas making these things. Yeah. It's not GE or any big names. It's just Joe Blow out of his backyard and making good living out of it too. This is not unique with hydro. If you have hydro plants dispersed around a province or around a region, they will not all have the same pattern. In South Asia, some of the rivers are mainly snow-fed, and the water starts to rise in mid-March or so. Other rivers depend on rainfall, and they have to wait till June until the monsoon arrives. So you've got this diversity helps to provide some firm capacity. If you are looking at wind and you disperse your wind farms around a big province like Ontario or Quebec, it's not, the probability of having slack wind everywhere is very, very low. So this is an interesting possibility, but it's not unique to hydro. I want to talk a little bit about the challenges to hydro, because this is an issue for developers. And I'll go talk to each of these points in turn. The footprint for hydroelectric developments can be very large. And this is the source of a lot of the the issues, if you have a very large project, the more impacts, more issues are likely to arise and that have to be dealt with. So if we look in small footprint hydro, we're talking run-of-river or multi-purpose, where the impacts are very small. But when you start talking about projects with reservoirs or diversions, projects that are remote, requiring long transmission lines and access roads, the impacts are quite a bit larger. The environmental effects, typically we're talking about inundation of the banks of a reservoir. This is mainly about the reservoirs now. Not only do you spill over the banks, but you actually, you destroy a shoreline environment. Of course, in time, a new shoreline environment creates itself at the new level. Hydrothermal change is not much of an issue most of the time, but if you create a reservoir where before you had a lake, you've got double the amount of mass, double the amount of water, and this affects the rate at which the lake cools in the fall and warms up in the spring. It affects the period with ice cover. And this is an issue to people in northern Canada who travel on the ice quite a bit. Biochemical, the two main things, and they're both rather unexpected to some extent, is the issue of mercury contamination. This was only discovered in the 70s because we didn't have instrumentation precise enough to measure parts per million. When water floods over land which is previously dry, a sort of mercury cycle is initiated, and a rather in which there's a fairly significant abundance of methylmercury. This is a mercury compound that's available for life functions. Its concentration in the water is still pretty low, but it's magnified through the food chain. So plants which draw in some mercury in their processes are then consumed by fish, and there's a factor of, I don't know, 10, 15. There's a big multiplier. The herbivorous fish, then they become prey for the larger fish. The larger fish get eaten by the giant fish. So by the time all these magnifiers are taken into account, the large-scale predatory fish, large-sized predator fish in the Northwest Territories would have mercury, or measured in the reservoirs for which I was responsible, mercury loads of between 1/2 and 3/4 of a part per million. At the time, I was in the Northwest Territories, perfectly safe for Americans, but not safe for Canadians. The Canadian standard was for consumption 0.5 part per million. American was 1. So it was okay for the Yankees to come up, going fishing up there. Sedimentation is, of course, an issue in parts of the world where the rivers carry large loads of sediment. In a more localized sense, sometimes during the construction activities result in localized erosion because vegetation is removed. Flow regime, if you have a reservoir, you will alter the flows and the water levels. You may alter the temperatures as well, but flows and water levels are the main thing. And the impact on biota, I'm thinking fish, waterfowl, and mammals. There are socio-economic issues in South Asia. A big one is resettlement. Not so much an issue in most of Canada. You know, I was responsible for 2 reservoirs, 2 basins. Snare Basin is about 25% bigger than my native country, Jamaica. Had one village of about 150 people in it. The Talson River system would have been 4 times the size of Jamaica. 0 population. So not such a big issue in Canada. Impact on water use, resource users, this would imply in some countries in Asia, flooding of agricultural land. In Canada, maybe impact on the fishery, and may have some effects on travel. Could be beneficial, could be otherwise. Health is not an issue in Canada, but could be in some parts of the tropical world. Reservoir development may increase the number of mosquitoes that carry malaria, though it generally reduces the number of black flies that carry river blindness. It's not a subject I really know very much about. At the end of the day, one should note the benefits. Power for hydro is, of course, the main benefit. There are other benefits that may accrue sometimes. The fishery in large reservoirs can be quite abundant. It's not that much a use in Canada. Because of this mercury stuff, for the Churchill Falls development, the general manager of Churchill Falls Labrador Corporation, Jack Beaver, he was a First Nations person. He thought, why don't we develop fishery to the benefit of the local people? That's when they discovered the mercury problem. But in Volta Reservoir in Africa, where the sociologists considered it very unlikely the locals would ever become fishermen, that huge reservoir, which is, I think, still the largest in the world, within, I think, 5 years of completion, 11,000 people made their living as fishermen. You know, the sociologists said these guys have been cultivators for millennia. You know, they're not going to be interested in fishing. Well, phooey. The folks were very adaptive. The tragedy was the reservoir wasn't prepared, and the possibility of having maybe 50,000 fishermen couldn't be realized. In countries like my little country of Jamaica, where there are no lakes, a reservoir is a site, you know, it's enjoyed for its beauty, and sometimes for recreation, except in Jamaica, the main reservoir is for drinking. And it's not doesn't kind of work too good for people to be seeing people swimming around the water supply. Especially when somebody went and fell in the goddamn reservoir and drowned. That really upset folks big time. Anyway, I thought we should just summarize the roles of engineers, biologists, and social science types in evaluating the impacts. I'm looking at the impacts as opposed to the design, and I'm thinking reservoirs more than just, a small hydro and run of river. The basic engineering input is fairly easy to do, is a simulation to characterize pre- and post-construction conditions related to flows and water levels. The design of mitigation options, I'm thinking of fish ladders, artificial channels, and water level control, weirs, etc., to minimize the impact of the development. The engineers, in dialogue with the biologists, can often mitigate potentially deleterious impacts by designing an appropriate operation strategy, controlling, keeping, making decisions about how the water is used. And when you have a large system with many reservoirs, you could optimize the use in such a manner that it minimizes effects on the environment. The biology, I see them taking the information produced by the engineers, and this engineer and I'm sort of promoting the idea of eco-hydraulics. The engineer describes the changes in the physical environment. The biologist then has to look at that and are these, what's the effect, what's the consequence? Are they bad, nil, or beneficial? The biologist is the best person to identify mitigation opportunities and to advise the engineer of design criteria that he needs to apply in developing any mitigation that is of a structural kind. Monitoring as-built performance versus actual is something that I think is necessary. There's a tendency to get all these mitigation projects done and then forget about it. That don't make a whole lot of sense. Socioeconomics, need to look at the socioeconomic. I'm thinking of initially the impact on the economy. What are the benefits created? What are the opportunities lost? Look at the social effects and strategies to minimize adverse impacts. We're increasingly looking at providing First Nation people with economic benefits. In Northwest Territories, by virtue of ownership of the resource, First Nations will be owners in any future project, at least partial or part owners. Evaluating and looking at evaluation and determination of compensation measures as necessary. I could rattle on about this, but I think there's a sense that the process is not as coherent as it could be. I think engineers would like to see some timelines. I think we like to see a kind of a roadmap, and we'd like to see some control of expenses. I mean, this can go on forever. So this is best discussed in questions if anyone has. Here we're coming towards the end. And they say I'm in a sustainable institute, so now I'm getting a real danger zone. But for me, the way you start looking at sustainability is defining what the hell it is. This is a definition which I find to be the most representative and intuitively the most appropriate. It says a sustainable project would be, or method would be such that harvesting or using the resource in such a manner that it's not depleted or permanently damaged. Now, this is a sort of a representation of a very detailed evaluation of the Hydro project that's just about complete. It's on the Rio Madeira in Brazil. It's a run-of-river project with a huge capacity, 3,750 megawatts. Rio Madeira is one of the largest tributaries of the Amazon. Using my description, essentially ups. This is the only element that I feel affects the sustainability. If you have sediment problems like you see in India and Nepal, after some period of time, those reservoirs are going to be full of gravel, and the utility of the project very much restricted. In Canada, so that is basically the first statement, that sustainability is largely about reservoir sedimentation. That in Canada, or shall we say Canadian projects located on the Canadian Shield, on the extension of the Appalachian Range, that's Newfoundland. Well, to start with, we hardly have any soil. And we have a terrain that's fairly flat, large number of bogs and lakes, with the result that the water entering the reservoirs is practically free of sediment. Will sediment be a problem? Well, not unless you're thinking about geological time, maybe 10,000 years or 100,000 years. So my final conclusion is that in talking about sustainability, we probably should be thinking about two kinds of questions. I think the sustainability issue goes back to that definition of mine, and practically concerns sediment. Acceptability deals with a whole bunch of other issues in which the authorities and the owners have to debate trade-offs. You know, you can't make a omelet without scrambling an egg, they say. So you have to look at the costs and the benefits, look at the extent to which adverse effects can be mitigated, look at the effects and opportunities for benefits beyond power, flood control maybe, as in Malaysia, recreation as in some other countries, and then a judgment ultimately on the overall acceptability of the project is arrived at. Now, a lot of that second part is political. You know, eventually you make your best arguments, and the politicians are going to decide their feeling of what the folks think and the alternatives, because maybe the average guys think it's a stinker, but if the alternative is nuclear, maybe you go with hydro. So that's basically my story. Oops, I better turn this off. And be happy to answer questions. The last time I was anywhere near there was when my mother died, because she came from Lucknow.
Oh, okay.
And so that was 1965, I guess, 64, long time ago. My Indian friends always were intrigued when I told them my mother came from Lucknow, was born in Lucknow. But they didn't know about Lucknow in Canada. Any other questions?
Just a couple. I'm going to ask a couple engineering questions.
Yeah.
And I'm going to
Yeah.
talk about the sustainability. I was just curious, the 50% capacity ratio on rivers, what's that, where does that come from?
Well, that comes from a study I did for a small project in Quebec. It ultimately is an outcome of an economic analysis. But we found quite widely in Quebec and Atlantic Canada that the economic size for a run-of-river plant that's operating as a fuel saver is about 1.5 times the mean annual flow at the site, or the 20% point on the flow duration curve. They're basically identical.
So the origin of that 50% is really the fluctuation in the river flow rate, and you have to spill some of it.
It's what you're able to put through the turbines. Where the inflow exceeds the capacity, then it's spilled. And we're looking at these as pure as basically conventional run-of-river without significant storage.
Now, you mentioned sort of a non-engineering question I was going to ask. You mentioned Quebec. Now,
Yeah.
the James Bay hydro projects, what do you know about those? Great Whale?
Well, the Great Whale was a subject of a lot of contestation. And I think, one of the things is my friends went down the Great Whale River and they found no portages. The river is, I think, historically not a travel route for the Cree because it's too rough, too many rapids and too many falls. what I think has come partly from that issue, that particular story, but I think from other actions on the part of large utilities. I think the large utilities, and Hydro-Quebec certainly a great example of that, and currently Nalcor in Newfoundland, they're big, arrogant organizations. And I think the public has come to distrust them. And this, I think, reflects inacceptability of hydro. We're kind of painted or tainted by this arrogance of the big utilities in the past few decades. And this sort of poses a kind of a technological challenge. No, a political challenge. Hydro starts off, the public thinks it's a scam, or it's going to be huge cost overruns, or it's going to be a environmental disaster. Now, when you talk about environmental disasters, there was quite an uproar over a small hydro plant in Belize, Cholilo project. And I picked this up on French television, discovered that the company I worked for, my clients downtown St. John's were in charge. And I said, my God, what the hell are you doing? You know, what kind of a reservoir have you got that's so important? Well, I was imagining reservoirs of maybe 2,000 or 3,000 square kilometers in extent. There's a tiny little reservoir of about 7 or 8 square kilometers. You know, the whole ballyhoo was way out of, disproportionate. You know, that was fellow, I'm not hot on movie stars. Newman, what's his first name? Paul Newman. He was trumpeting that. He got they got on board some geologists from the oil patch who said the foundations were crap. But what the hell do they know about dam foundations? You know. So anyway, I've got off a bit. So repeat the question.
So the basic question, I guess, is you answered part of it.
Yeah.
Sort of the political side of how the hydro companies work. What do you think the future of exploiting the hydro in northern Quebec therefore is because of the bad?
Well, I think Hydro-Quebec has sort of hit a wall. They're working on the Romaine River. It's remote, and the sites are not as favorable. I think many more sites for a total of about 1,000 megawatts. So the topography is less favorable, unit costs are higher, remoteness is a factor. I have a strong suspicion that Hydro-Quebec may not be building many more big hydro because it kind of hit a wall. I worked briefly on the Sarcelles project in Quebec, which is a very low head project with a capacity of about 120 megawatts. And the price tag I heard banded about of $800 million. Now, the economics stink. Now, if you go on Hydro-Quebec's website, they credit all the downstream benefits from this diversion. So it's a diversion ultimately from the Rupert River and the East Main River through Reservoir Opinaca into LG2. They're crediting all the extra power downstream, so it looks okay, but it's false. It's just so crooked. It's crooked as a $3 bill, they say.
I was wondering if you could go back to the spider diagram you showed.
Yeah.
I just have 2 other questions.
Okay, so
Okay, so the first question is going to be related to what you're defining as
Yeah.
sustainability, erosion, and sediment, and just what I've heard and what you might know about the truth. The Three Gorges Dam in China,
Yeah.
how sustainable is it by your definition?
Uh,
Because I heard that sediment might be a problem.
well, the sediment will be a problem. The Chinese are planning to install gates, openings in the bottom of the dam. And my understanding is that during the flood season, they're going to lower the water level so as to be able to flush a considerable amount of the inflow. So they're going to, again, this is, don't quote me on it, but the impression I got is they're willing to trade off quite a bit of energy generation each year in order to keep a significant amount of the reservoir as viable. They won't be able to flush all of it because it's just a bit too much. It's, I don't know, a couple 100 kilometers long. But I think they'll keep about 30% of the live capacity, something like that. When you come down to a run-of-river dam, with a run-of-river project in the Himalayas, for example, you can flush pretty well all the sediment out because the dam is only, 5 to 15 meters high. When you open all the gates, it's like you don't have a dam there at all. You can get most of it. So the small hydro in those environments is still sustainable.
So is it true that the Three Gorges Dam is going to lose its capacity over time?
It will, but if I am to understand the operation, they're operating in such a manner that they'll keep a useful percentage of it. They're not going to let it fill up to the brim, in other words. And so my understanding is that they've done a lot of modeling, mathematical work to determine sort of a balance. Because if they maximize the recovery of storage, it may cost too much in loss of power. Right. If they maximize power, they're just guaranteeing that after 50 years or something like that, they'll just have a run-of-river plant.
Okay. The last question related to sort of your definition of sustainability. I was a chair of the water treatment quality PhD defense this morning. And I can tell you, water quality was seen as a very strong sustainability issue. Because without that, you don't have people drinking water. So I was just wondering why you wouldn't include water quality within your sort of engineering definition. And it was a civil engineering defense this morning.
I guess the reason I don't is just my experience is that water quality is not a problem with Canadian reservoirs, by and large. In places where it is a problem, there are some potential for mitigating it. Most Canadian reservoirs, especially in these Canadian Shield, are relatively shallow. They don't look much different from natural lakes. And with the cold, with our wide seasonal variation, we have all our reservoirs in Canada, all our lakes virtually, will turn over. The temperature will be reduced to 4 degrees. The water at the bottom comes up to the top, so that this prevents having a bottom layer of deoxygenated water. Now this is an issue in subtropical countries, some parts of the United States, especially in deep reservoirs.